A beautiful relationship between Stirling numbers that sadly I never had. Okay, um, here are these three infinite sum formulas, right? And we are gonna prove just the third one actually because I have already proved the second one in one of my previous videos, which I will link in description. And the first one is just similar to second one. This first one, this number is the Stirling number of first kind, right? We have already talked a lot about this. Maybe I will link a couple of videos. Uh, the one introducing Stirling number of first kind, the one introducing Stirling number of second kind, and the one proving this sum in the description so that you can check them out and then get familiar with it. Stirling number of first kind, and this is Stirling number of second kind, right? Yeah, and this one has been I've already proved, right? This sum from k equals to 0 to n of this Stirling number of first kind x to the power k is rising factorial. If you don't know what rising factorial, this is x plus 1, like the number is rising, and it goes up to x plus n minus 1. There should be n terms over here. N terms. Similarly, there's also a thing called falling factorial. This is x minus 1, and this goes up to x minus n plus 1. Again, there are n terms over here. Okay, this is the idea. And yeah, so this is actually, to be more specific, unsigned Stirling number of first kind, because this doesn't really have a sign. All of them are just positive numbers. And there's also idea of signed Stirling numbers of first kind. So basically, signed Stirling numbers uh have this minus 1 to the power n minus k with them along with this expression, right? And x to the power k, and this comes out to be x to the power falling factorial n, right? Okay, and this is signed Stirling number of first kind. Okay, now, and there's another interesting expression. Like if you just swap this falling factorials and x to the power k, like that relation also holds true for Stirling number of second kind. And personally, I felt that's so amazing because like for this Stirling number of second kind, now if you have this falling factorial, the expression is just x to the power n, and like that's so beautiful. Like I mean, like at first like glance, when you know when you just know the definition of these Stirling numbers of first kind and second kind, like you cannot really guess that there would be such a beautiful relationship between those two numbers, and turns out there is. So that's actually cool, right? And we are gonna prove this in this video, and yeah, and then get satisfied. Okay, let's see how we can prove this. We're actually gonna use the recurrence relation of Stirling number of second kind that we already derived. So the recurrence relation is this number will be equals to k times Stirling number of second kind n minus 1 k plus n minus 1 k minus 1. Okay, and what we're gonna do is, first of all, let's just multiply all of them by this falling factorial. Yeah, and then let's sum it up. Let's sum it up from k equals to 0 to n. Yeah. Okay, and then yeah, sum from k equals to 0 to n of n minus 1 k minus 1 x to the power k, right? Okay, now this is the expression that we actually want to find, right? So let's say that expression, which is a function of x and n, right, to be this f when we want to solve for f. Okay. Okay, over here, the one of the problem is over here in this sum. The sum is in the world of k, right? So k is not really a constant; that's a variable. And we need to find some expression for k x to the power or like this, which is a bit nicer. You can actually do it in the following way. Notice that x to the power k plus 1, this expression is just x minus 1 up to like x minus k plus 1, right? And then one more term, right, which is x minus k. So there are k plus 1 terms over here. And similarly, like x times x to the power k is going to be x, and then x minus 1 up to x minus k plus 1, right? So over here, if you take difference of x to the power k and x to the power k plus 1 falling factorial, like all these terms will be common terms, right? So those terms are just x to the power falling factorial k. And then here, if you have x extra minus over there, you have x minus k extra. So notice that that's just k x to the power falling factorial k. So from here, we have an identity that this k times x to the power falling factorial k can be written as x times x to the power k falling factorial minus x to the power k plus 1 falling factorial. And that's what we're going to use, this property. So we will have f of x comma n as sum from k equals to 0 to n, and then this n minus 1 k, and then k x to the power falling factorial k is the remaining expression, which can be written as x times x to the power k minus x to the power k plus 1 falling factorial. And for now, we write the other expression as it is, and we will notice something now. N minus 1 k minus 1 x to the power k. Also notice that because at k equals to 0, this expression is invalid, right? So I can just take the sum from 1 to n, right? Because it k equals to 0, that n minus 1 minus 1, that's just defined to be 0. And so this becomes n minus 1 k minus 1 x to the power k, right? Now if I want to take it from, let's say if I want to again take it from k equals to 0, I can do this, right? I can take it from 0 to n minus 1, right? And then just make it k and make it k plus 1 over here, right? I can do that, right? Okay, so now this is a bit nicer. Now we have f of x comma n, and then this is sum from k equals to 0 to n. We have x times n minus 1 k, or x to the power falling factorial k, minus sum from k equals to 0 to n minus 1 k x to the power k plus 1, right? Yeah, and then we have plus sum from k equals to 0 to n minus 1, right? Yeah, we're just let me confirm that first. Yeah, okay. And then n minus 1 k x to the power k plus 1, right? Okay, so now over here, notice that in this expression, since there's this n minus 1 with k, so at k equals to n, while this form is in k equals to n, this k will be bigger than n minus 1, right? So the last term will just be 0 because that's just invalid and that's defined to be 0, right? This becomes f of x comma n is equals to x, and this is now just f of, over here also, the last term will be 0. So this is effectively same as sum going from k equals to 0 to n minus 1, right? Because n minus 1 with n, that's just 0, right? This thing over here will just be 0 because k should be less than this upper expression. The lower number should be less than the upper number. And then x to the power k falling factorial minus, this is also same thing, from k equals to 0 to n minus 1 k x to the power k plus 1 plus sum from k equals to 0 to n minus 1 k x to the power k plus 1 falling factorial. Now notice that I can actually cancel the last two expressions, and that is a really beautiful thing because that simplifies things a lot. Now this is f(x, n). Notice that over here, everywhere n is replaced by n minus 1, so this is just f of n minus 1 comma x, right? Sorry, f of x comma n minus 1, right? Okay, now that we know this recurrence relation for f, and also we can actually find f of x comma 0 which will just turn out to be okay. If I take this, only the first term will be non-zero, which is first term will be 1, so this is just 1. And so from there, f of x comma 1 will be x times f of x comma 0, and this is just 1, so just x, right? So f of x comma 2 will just be x times f of x comma 1. F of x comma 1 is just x, so x times x, which is x squared, right? F of x comma 3 will be x times f of x comma 2. F of x comma 2 is x squared, so x times x squared, and it's x cubed, right? Now again, go on like this, and again you can use induction to prove that x comma n is just x to the power n. By that, we can prove using induction that f x comma n is x to the power n, and this was exactly our required sum from n equals to sum from k equals to, I guess, from k equals to 0 to n of n k x to the power k following factorial. This expression over here is x to the power n, and we have proved that. We have proved this really beautiful formula. Okay, guys, so this basically involved the recurrence relation and then trying to get this property for kx to the power following factorial k. And then after that, there was some cancellations, and it was a simple recurrence which could be solved easily. So that was it, guys, and I hope you also love this relation. And then, yeah, get surprised with the beauty of maths and keep enjoying maths. And I look forward to seeing you in the upcoming videos too.